Hello, welcome back to Math 100. We are starting another new chapter, chapter 13. And the topic here is the nature of probability. Okay, so as usual, let's go over the definitions. Okay, an experiment is an observation of any occurrence. So it's very much kind of like your biology or your chemistry experiment that you would do something and record the result, right? So do an activity and record the result. Okay, it could be multiple, right? And the sample space is the set of all possible outcomes from the experiment. And so, for example, if your experiment is to flip a coin, right, or roll the die, and all the possible outcomes of flipping a coin, which is what head or tail, right? Head or tail, and that will be the sample space. And if it's to roll the die, then it will be what 1, 2, 3, 4, 5, 6, and that will be the sample space. Okay, so an event is a subset, very important, a subset that you choose, right, from the sample space, and it's often denoted by the E, right? The sample space is denoted by S, and it's representing a very specific outcome, okay, very specific characteristic. So, for example, the event could be a head or an even number, in rolling a die, okay, and the sample space is always everything, and the event is a subset. That's very important. Okay, so a simple event then here is the possible occurrence of one single task, right? So, for example, if you flip the coin once, that's a single task, and then the compound event will be multiple, right? Multiple tasks, like flipping the coin 3 times. But it doesn't have the compound event doesn't have to be repeated, one action repeated multiple times. It could be flip a coin and roll the die, right? So it's just more than one task. The task doesn't have to be the same task repeated, okay? And then the probability, because the probability is counting the chance of something happening, so it is going to be a decimal or a fraction, okay, between 0 and 1. And why is that? Okay, because when we're counting the probability of something happening is like 2 out of 3, 4 out of 5, right? So we can have like 6 out of 5, for example. If you only have 5, how can you have 6 out of 5? And so it doesn't get bigger than 1, right? Because usually the denominator is all the possible happenings, possible elements in the sample space. So the numerator is usually the event, and event is a subset of the sample space, and so that's why event is smaller than the sample space cardinal number-wise, right? So you cannot have a probability that's bigger than 1. And you cannot have a negative either, because when we count, we are counting whole numbers, so that's why it cannot be less than 0. So it has to be somewhere between 0 and 1. Rarely will we get a probability of 0, and that we call an impossible event, because the event that has a probability of 0 is like drawing a red club card. Remember club card, in a deck of 52 cards, we have the diamond and the heart that's red, and club is black. Club and the spade is black. So you can't have a red club card because it's contradictory, right? Club card is black. And so that's called a impossible event, and impossible event has a probability of 0. Okay? A definite event means it will for sure happen. And so, for example, for sure tomorrow the sun will come up from the east and not from the west, right? And so for sure something will happen. It's called a definite event, okay? And that will be the probability of one, because one is what, 100%. Okay, one is 100%. All right. And the next definition is called the subjective probability. Okay, subjective probability, when we say something is subjective, we say like English is subjective, math is objective. So, math has an answer most of the time. An answer we can all agree on is called objective. Subjective is more like a personal opinion, based on, past experience, the way you interpret things. Everybody interpret different ways differently, So, the subjective probability is based on the past experiment or past experience. It indicates the nature of certainty on the speaker's part, like a dad saying to his daughter that after the outburst, the probability of you going to the prom is almost zero. So that's kind of like the dad's personal opinion of something happening. Okay, so subjective probability is almost kind of like, I would say, what, maybe like a fortune teller, maybe. Okay, fortune teller is maybe an example of a subjective probability based on, the speaker's experience. Okay. In this class, however, we're going to focus on the theoretical probability. Okay, so theoretical is more like probability we can all agree on, and most of the time theoretical probability is drawn based on the a lot of experiment, and we compile and we kind of learn from the experiment and have a model, and we can all agree on, and that's called the theoretical probability. And I call that the ideal probability. Okay, the ideally that will be what happened. For example, if I flip the coin 2 times, ideally is one head and one tail, right? The 2 times. So half of the time I will get a head and half of the time I will get a tail. But if I actually do the experiment, I may not get exactly that. So theoretical probabilities, ideally that's will be what happened. And we calculate the probability of the event, that's the description of the event in the parenthesis, by the cardinal number in the numerator, cardinal number of the event in the numerator, and the cardinal number of the sample space in the denominator. And because E is a subset of S, and so the cardinal number of E is less than the cardinal number of S. And so the numerator smaller than the denominator. Again, that's the reason why probability is usually less than 1, right? So when it's equal, then you get 1 over 1, or 2 over 2, or 3 over 3, or 4 over 4, or 5 over 5, and they all simplify to be 1. And that's why the probability of any event, biggest number you can get is 1, right? Remember 4 over 4. If you have everything, right, event is exactly everything in the sample space, then it will all simplify to be 1, right? They all simplify to be 1. So that's the biggest it can be. All right, so the empirical probability is the last type of probability, and the empirical actually derived from the word experiment. So empirical is the number of ways an event occurs in an experiment divided by the all the possible outcomes. So, for example, if you are in your physical class, and maybe there's 50 students in the class, and I ask you guys all take out a coin from the pocket, from your pocket, and then flip a coin. Everybody flip, okay? And then tell me, student A, what did you get? Student B, what did you get? Student C, what did you get? And I record all the result out of, all the possible outcomes, and hopefully I get 25 heads and 25 tell ideally, but if I don't get that whatever result, if let's say if I have 50 results, right, and so I only had say 20 heads, and so that will reduce to be 2/5, right? So it's not always half, right? It's not always half. Ideally, it will be half, but the experiment, recording the actual happening, that's called the empirical probability. And so we don't do empirical probability in our class because we don't have time to tell everybody to do the experiment. Okay, so we will try to do the theoretical results in our practice. However, we understand that the law of large number, meaning that even though the empirical probability, each time you do it is different, but if you keep doing it, you do a lot of it, it will actually get closer and closer to the ideal probability. Okay, so don't be so worried when your result is not exactly what the ideal probability is going to be. Okay, so when you are doing the experiment, repeat it more and more times, the empirical probability, the proportion of the outcome, variable outcome, will tend to come closer and closer to the ideal probability of that event. Okay, so again, when you are recording your results and it's not exactly the same as what the book says, the theoretical probability, what the formula says, it's okay, because if we do it enough, it should agree or get close. Okay, so that's what law of large number means. Okay, all right, so let's do some practice, and hopefully what we have said over there can make more sense after we do the practice. Okay, so practice number 1, if you roll a 6-sided die, a regular 6-sided die not weighted, okay, once, what is the probability of rolling a 4? And so probability, we write the event in here, whatever your event in the parentheses, right? So to describe the event, so in this case, our event is to roll a 4, right? So we will count the sample space, right? Sample space is, no restrictions. What are all possible outcome of rolling a die, right? So all possible outcome of rolling a die, you can roll the 0, so start from 1, 2, 3. You can roll the 4, you can roll the 5, you can roll the 6, right? So that is the sample space. And the cardinal number of the sample space is 6, right? 6 possible outcomes. And the event is described in the parentheses, right? So the event is rolling a 4. So out of, again, event is the subset of the sample space. So out of these 6 choices in the sample space, only one of them is 4. Okay? And so my sample space is 6, and my event, the cardinal number, I forgot the cardinal number of the sample space is 6. Cardinal number of the event is 1, right? Remember what cardinal number is? And so the probability of my event will be the cardinal number of the event divided by the cardinal number of the sample space. And so it will be 1 out of 6. Okay? Hopefully that makes sense. Okay, so number 2, we are still rolling a regular 6-sided die, right? So, but our characteristic of the event that we are looking at is a little different here. So our event is going to be what? Roll A4 or A5, right? Again, it's in the parentheses. The description of the event is in the parentheses. And so our sample space is the same because the action is the same as rolling a die. So the cardinal number of the sample space is still 6. But now the event is 4 or 5, right? So 4 fit the characteristic 4 or 5. And so our cardinal number now changed to, the cardinal number of the event now changed to 2, right? So then I have 2 out of 6, right? Because, oh, I skip a step. I should write the event over the sample space, right? So that's the event is 2 and the sample space is 6, right? You agree? And then we always want to keep our answer in the lowest fraction if you want it as a fraction, so it will be 1/3. Okay, and if I can reduce, what should I do? If I can reduce, I don't know how to reduce. Would the decimals help me? Okay, the graphing calculator. So let's see. Oops, let's see the graphing calculator here. So if I type in 2 out of 6 divide, that is 0.333, but because it's everlasting decimal, I don't want to cut it because they didn't tell me to round it. I don't want to cut the decimal into, like 2 decimal place or something like that because I was not instructed to do so. So how do I keep it as a fraction that's more accurate? And so all I do is put my cursor to this blue part and then press it, and then you will reduce for me 1/3, okay? And if you want to change it back to decimal, you click it again. It will change between the decimal and the fraction. And the fraction is always in the lowest term, meaning simplify. So that's how you can use decimal to do the fraction reducing for you if you don't want to make a mistake. Okay? Hopefully that makes sense. Does that make sense? Okay, so back to here. Number 3, 156 show. Is this an element or is this a cardinal number? Okay, it's very different. Number 6, in rolling a die, is an element, but the, number 5 is an element, right? Number 4 is an element. That's different from the cardinal number. The cardinal number is count of elements. So make sure you know the difference. So here, when we say there are 156 shows in the Netflix, if there is everything, and so that will be the cardinal number of the sample space. So 156, right? So if I have the sample space equal to 156, that means what? That means the cardinal number of the sample space is 1. So make sure if it's element, then your sample space, the cardinal number is only 1, right? So make sure this 156 is not the element, it is the cardinal number, right? So the 87 of those shows suck. And so the event is the show that suck, right? So again, that is the cardinal number. So that is 87, right? So we don't know what is the name of the show that suck, or all 156 shows, what are their names, right? So the name will be the element, but here, what is given here is the cardinal number. We don't have all the names of the shows, so we can we can list all the elements in the sample space, but we got the cardinal number, and that's all we need, right? So the probability of the shows that suck, right, is the event, the characteristic, and so we will take the cardinal number of the event over the cardinal number of the sample space, which is already given. So it's 87 over 156. And here it does tell us to answer in decimal and change it to the nearest 2 decimal place. And so we're going to follow the direction, right? Make sure you follow the direction. And so we're going to make this 87 out of 156, right? And it gives us the decimal, and because we want to round to the nearest 2 decimal place, I look at the third one is a 7, so I'm going to add 1 to the hundreds place before I drop the 7. So it's going to be 0.56, right? And it's less than 1. That's between 0 and 1. That's good. But if I wanted to keep it as a fraction, if they didn't tell me to write it as a decimal to, keep it at 2 decimal place, then I cannot cut the decimal. Then it's not accurate anymore unless I'm instructed to, right? So preferably, if you have a long decimal, you want to keep it as fraction, so we'll click here again to keep it as a lowest term in the fraction. To keep it as fraction is more accurate than to keep it as a decimal, because decimal, when it's long, unless they tell us to cut it, if you cut it without being told to, then you kind of sacrifice the accuracy of your answer. Okay, so you don't want to do that. Okay, so we're going to follow the direction. It says to change it to the nearest two decimals, so it was 0.556 or 923 ... right? So it's approximately 0.56. Follow the direction. If it didn't tell you to cut it, don't cut it. Just keep it as fractions, more accurate. Okay? All right, number 4. It says in a class of 30 students, 4 of them will not pass. So if a student is selected randomly, what is the probability that they pass, right? So probability of the event is what? Event is pass, right? It's pass. It's not pass, right? So make sure you know what the event is, right? So your sample space is what? The cardinal number. This is a cardinal number already, right? The sample space is all the students in the class, right? I don't have the name of the student. That's the element. The name of the student is the element, but the 30 is the cardinal number of the sample space, right? And it says 4 will not pass, right? So 4 is the complement of the event, not pass, right? So the cardinal number of the complement is 4, so the event itself, because the event is pass, right? So it's either pass or not pass. So you have 30 students, 4 will not pass. What does that mean? That means your event will be what? Have a cardinal number of 26, right? Does that make sense? Because this is not the event, right? Not the event. And so again, the probability will be the cardinal number of the event over the cardinal number of the sample space. So just making sure you know what number to put in, right? So 30 is the sample space, is always cardinal number of the sample space is always at the bottom. And the top will be, okay, watch which one? 26, right? And so again, if they didn't ask you to round, you want to make sure you keep it in the lowest term in fraction if they didn't ask you to round. Okay? Or if it's like half, it's equal to 0.5. If it's a short decimal, it's not, if I don't have to make the decision whether to cut the decimal or not, then decimal or fraction doesn't matter. But if the decimal is long, and I was not instructed to cut it shorter, then it's better to keep it as a fraction. Okay, does that make sense? Okay, number 5. Number 5, you what? You are rolling a die and toss a coin, right? So this is task 1 and task 2, right? So what is the probability of getting a head and then an even number, right? So this is almost like the in chapter 12 we have this called the fundamental counting principle, right? So it still apply, the counting principle still apply, okay? And so let's talk about this. Probability of the event is what? A head, right? Then the tail. Then an even number, sorry, not a tail. An even number. I have to control my tongue. Right? So you have to know what is the element in your sample space, or for the cardinal number of the sample space, right? So if we were to have time to write it out, the events or the sample space, it will be what? The first one is going to be like head and 1, head and 2, right? Head, roll, flip ahead and roll the 1, flip ahead and roll the 2, or flip ahead and roll the 3, flip ahead and roll the 4, flip ahead and roll the 5, flip ahead and roll the 6, right? Or flip a tail and roll the 1, flip a tail and roll the 2, flip a tail and roll the 3, flip a tail and roll the 4, right? And flip a tail and roll the 5, flip a tail and roll the 6. How many are there? Can I count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so that is our old-fashioned way of counting. This is a sample space, right? So the cardinal number of the sample space is what? 12. That's what we counted. But is there an easier way, right? The fundamental counting principle tells us if you have compound event, right? And so compound event, your first one of tossing a coin, head and tail, you have 2. And then rolling a die, you have 6, right? So you agree with what we list down. So your probability or your cardinal number of the sample space is 12, just like what we had, write it, right? So how many of these is probability, is the event, right? Subset. The event is always a subset, and the event is a head and then the even number, right? A head and the even number. So a head and even number, this one is a head and the even number, this one is a head and the even number, and this one is a head and the even number, right? And so according to just counting our event, the cardinal number is what? 3, correct? But if we were to do it by the counting that we learned in chapter 12, the fundamental counting principle, the event that is ahead, we only have 1, right? And then times the even number in the die, we have what? 2, 4, 6, right? So that's 3, right? So the two event, the first event is a head and the second event is a even number. So we can use the counting method that we learned in chapter 12 for this too, right? So it's agreeing with what we say here. We can actually count it, we get 3 out of 12, or we can use the fundamental counting principle or the other counting methods that we learned in chapter 12 to count the event and then count the sample space using what we learned in chapter 12 and put it as a fraction. Does that make sense? Okay, so then what happens after that? Then we have to reduce, right? Because they didn't ask us to put it in decimal or to round, so then we will reduce 3 over 12 as 1/4. And again, if you don't know how to reduce, ask the graphing calculator for help. Okay, does that make sense? Okay, I hope it does. Okay. So let's move on. Number 6. Okay, so number 6, if you roll 2 die, is this a simple event or is this a compound event? You roll a die once and then you roll another die, right? So there's 2 actions. And so 2 action means what? You have 2 tasks, and so that's a compound event, right? So you want to have the event to have the sum of the dice to be 5. Okay, so first you need to kind of have an idea of what the sample space look like, right? The sample space is going to be you roll 2 dice, right? So it's going to be two numbers, right? So it could be 1, 1, right? 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, right? And then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. That's a lot, right? 2, 6. Is there any better way to, I mean, this is listing it down, but is there a good way to count the probability, I mean, the cardinal number? Okay, so the cardinal number is all the sample space, and we can again use the counting methods, right? Because we roll the die 2 times the first action is what the first one is. First task is 6, right? And then the second task is another 6, right? So we can keep listing it that way, or we can use the fundamental counting principle, right? 6 times 6, we know we have 36. We have 36, right? And then we want to know how many of this 36 actually give us the sum of 5, right? So I see 1 here is 1, 4, right? So if I keep going like this, I'm going to have what? What's the next one that's going to 1, 4, start with 1, right? And then if it start with 2, it will be 2, 3 is another one that's 5, right? And then I can do 3, 2, right? That's a different one because you use 3 in your first row and 2 in your second row, right? And then I can have what? 4, 1. So sometimes you can use counting principle, but adding to be 5 here, you can't really use counting principle for how you add to be 5, right? Because it's not exactly a pattern. It's not 2 different description there. So is this all the ways that you can do to add up to be 5? Any other way that you can think of? Right? So it can be 5, 0 because there's no 0, right, in the outcomes. And so I think this is 4 out of the 36 in this sample space fits our description, right? So remember the event had to be coming from your sample space, so you can't make up the outcomes for your event somewhere else. It had to be drawn from the sample space. Okay, so again, that's 4 out of 36, and so that will be reduced to 1/9. Okay, 1/9. Hope that makes sense. Okay, so this one is again roll 2 dice, so I can keep this sample space here, right? So the sample space is the same, and so it's going to be 6 times 6, which is 36. But out of this, is there anything, 1 plus 1, 1 plus 2, 1 plus 3, the sum of the 2 die, is there any one out of this sample space, right? The event had to be subset of the sample space, cannot be something I make up somewhere else. So from this 36 choices that if I keep listing, would I get a 0 for the sum of the 2 die? Would I get a 0? Is there any one of them that will get a 0, will give me a sum of 0? I mean, not 0, sum of 1. Would it give me a sum of 1? I would need to have like 1, 0 or 0, 1, right? But I can't have a die. I don't roll a die of 0. That's why I keep saying 0. I can roll the die of 0 to get a 1, right? To get a sum of 1. And so this is 0 because there's no element in the sample space fit that characteristic, right? So then that is anything 0 in the numerator give you the 0. So this is a impossible event. This is an impossible event, right? And same thing with number 8. Can you get the sum of 13? Okay, you can't get sum of 13. You can only get what? 6 and 6, that's the biggest sum possible, can be bigger than 6 plus 6 is 12, can be bigger than 12, right? And so again, you get a impossible event. Every time you have a numerator 0, it doesn't matter what your denominator is, the fraction will simplify to be 0. Okay, does that make sense? Okay, I hope it does. Okay, and for the next few questions, we are talking about the deck of cards. And if you forgot how a deck of cards look like, maybe you should search on the internet. There is 13 diamonds, 13 club. Club is black and heart is red, right? Heart is red, diamond is red, club is black, and spade is black, right? And in each of the suits here, we have ace is 1, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. And jack is considered 11. Queen is considered 12. And king is considered 13. And that's why 13 times 4 suits is total 52. Okay? So again, if you haven't seen a deck of cards or forgot how it looks like, look it up in the internet, and we can do this problem after that. Okay, you need to know how it looks like. Okay, and remember the deck of cards when we were counting in chapter 12, order does not matter. And so in a poker, there are 2 million something. We did this in chapter 12, right? So it's obtained by 52 combination 5 or 52 choose 5. That's where this number comes from. And if they already counted the event, the cardinal number of the event, the stray in this case, you have 10,200 ways to get a stray. If they already give you the cardinal number, you don't have to overthink it, right? So the probability of getting the stray for number 9 is just the event is the number of stray, right? This is a cardinal number, right? That's not the event, right? 10,200 is not the event. The event is that the 5 card hand, this down, right? So this is counting how many that fits the description called stray, right? So you already have the cardinal number of the event, so don't overthink it. Just take the 10,200. That's the cardinal number of the stray, and the cardinal number of all the possible hands without a specific characteristic is, we did that in chapter 12, is 2,598,960, right? And you can, again, get help from decimals to get you the answer in reduced fraction or in decimals. In reduced or approximate decimals if they ask you to round. And since they didn't ask us to round, we'll just use decimals to help us reduce. And I did that earlier. So this is the reduced fraction if they didn't ask us to round. Okay? All right. And number 10. Okay, the probability of 2 or a king, right? So again, how many you are only playing a single playing card, not 5, right? So it's not 52 choose 5, it's 52 choose 1. Or a single event, you don't need choose permutation or combination. It's just your sample space is your possible 52 cards, right? So your sample space, because it's one card, so it's different from the 5 cards in the hand of, a poker, right? So this is only one card, so your sample space, the cardinal number has changed, right? And so the denominator is 52. You agree with me? And now we just have to count how many 2 or king, right? How many 2 or king, right? So 2, I have what? 2 of diamond, 2 of club, 2 of 2 of heart and 2 of spade, right? So I have how many 2s? I have 4 2s, right? 4 2s. And then how many kings do I have? Right? How many kings do I have? King of diamond, king of club, king of heart, and king of spade, right? So altogether, I have 8. So that's the event, right? This is the event. This is the event. And so altogether, the cardinal number is 8. Okay, hope that makes sense. I should say event cardinal number, so that's 8. And we need to reduce, and that reduce to be 2 out of 13. Does that make sense? Okay, because we have 4 suits and each suit has a 2, and each suit has a king too. Okay. So that's OR. OR is if it either have a 2 or have a king, right? But AND, remember what AND is? AND is it had to be a 2 and a king. Does any of the 2 is also a king? Does any of the 2 is also a king? None of the 52 card is a 2 also a king, right? Because remember we are choosing one single card, right? You are choosing one single card. A card cannot be a 2 and a king at the same time, right? You cannot be that. And so that's why every time you don't have element, the event, cardinal number of the event is 0. I don't care what the bottom is anymore, right? So then the probability of the event, if the top is 0, then the whole fraction doesn't matter how many elements in the sample space, the probability will simplify to be 0. Is an impossible event. It's an impossible event because you don't have a card. Remember, we are choosing a card. And it can be a 2 and a king at the same time. No, it cannot be, right? Single playing card, right? So that's important. Single. One card cannot be a 2 and a king at the same time, right? And then number 12. Number 12, you again is one single card, so you only have 52, right? Your sample space is still 52 because it's not, 52 choose 5, right? And so you have that card that can copy a queen and a spade. Okay, a queen and a spade, or a spade. Sorry, queen or a spade. Queen or a spade. So another way to count, we already know the denominator because the cardinal number of the sample space is 52. So to count the event, right? The event is queen or spade, right? So how many queens is in the 52 card? How many queens is in the 52 card? Okay, so again, if you don't have the card in front of you to look at, you should get one and from the internet and count how many queens are there. Queens is number 12, right? So you have number 12 in each of the suits, so you have 4 queens, right? And the 4 queens are queen of spade, queen of heart, queen of diamond, queen of club, right? So 4 queens. And then how many spades do you have, right? So 13 spades from ace to the number 13 card. So you have 13, but one of them is overcount, right? So you can add it, but one of them is overcount, and that overcount because it's counted in queen of spade, right? And also count in the spade, so I have to subtract 1. The one that is overcount is the queen of spade, right? The one that is overcount is queen of spade. So when you add, you have to remember to double check if you have any overcount, it will be taken away by subtraction, right? Because you counted by adding, so you will take away by subtraction. And so 4 plus 13 minus 1 will give us the 16. Is it 16? 16 out of 52. And can 16 out of 52 reduce? You can ask decimal. Okay? So it's going to reduce to 4 out of 13. I asked decimal earlier. Okay, and I hope that makes sense. Okay. Okay, how many more questions? Okay, about what, 5 more? About almost there. Okay, almost there. So again, this is one single car. Every time we're drawing single car, the sample space is easy to find. It's again 52, but can it be a queen and a spade? Queen and a spade is what? You have both characteristic, right? You have a car with what? Both characteristic. Versus number 12, you have a card that has either a queen or spade, either or characteristic. This one has both characteristic. It's only queen of spade. Only queen of spade have both characteristic, right? So it's 1 out of 52. And again, the 52 is because we are still drawing one single card, still the same denominator, same sample space. But this one here is because you only have one queen of spade in that 52 card. And 1 out of 52 is the lowest term, so you can reduce. That is the answer. That is the answer. Okay? Does that make sense? Okay, number 14. Okay, when I see this big number here, part of me is scared, wow, huge number, but part of me is, that's cardinal number, right? They counted it for me. I don't have to count, right? So it says there are 1,098,240 ways to get a single pair, right? So this, again, is the total possible hands in a poker. So what is the probability of getting a one pair, right? One pair is one single pair. And so the cardinal number of that one single pair should be on the top, right? Because that's the even event, right? That's the event. That's a specific characteristic is one pair. So that should be on the top, 1,098,240 of the event, the cardinal number, and divided by, again, this is 5. Where does this number come from, right? 52, choose 5, the 5-hand poker, right? So it's 2,598,960. Again, we did that in chapter 12. And we would use decimals to help us. It says to round to the nearest 2 decimal place, right? So we would take out the decimal graphing calculator and help us do that. Okay, so again, remember how do you do that? Let's take out the decimal. It will be 1,098,240 divided by 2,598,960. Did I do it right? Okay, so they wanted 2 decimal place, the nearest 2 decimal place, so it should be 0.42 because the third decimal place is small, right? The third decimal place is small. Where did my problem go? It jumped to the top. Okay, so my problem was 0.42. Do we say 0.42 because the third decimal place is small, right? Approximate. It was 422, right? So it's 0.42, right? Something like that. Let me double check again. Was that? Yeah, 0.42, right? Okay, so number 15. Okay, 3 more questions. So what is the probability of having precisely one boy in a 2-children family? right? So 2 children, 2 actions. Hopefully, unless you have twin, you have to give birth 2 times to have a 2 children family. So your cardinal number of your sample space, you can use it by fundamental counting principle, right? So you can have boy or girl, right, in your first child, so 2 choices, and then you can repeat the same sex in your next child, and so you don't lose a choice. So that's fundamental counting principle, and that should give you 4 choices. And if you like, you can actually write 4 choices out, because it's 2 actions, so it's not going to be B or G, right? It's going to be BB, BG, GB. It's 2 actions, right? So it's 2 letters, right? And GG, right? So 4, that's where the 4 come from, right? So this is our sample space, and that's why the cardinal number is 4 for our sample space. And which one out of the sample space? Again, the event had to be subset of the sample space. So it cannot be something you make up. It had to be from the sample space, right? So which out of this 4 is one boy, right? So it's the BG and the GB, right? So it's from the sample space. The event had to be a subset of the sample space. And so that is giving us the 2. And so probability of having one boy in this 2 children family is going to be what? 2 out of 4, or 1/2. Does that make sense? Okay. And number 16. Okay, so sample space now, I can reuse the sample space because this is now a 3 action, right? 3 children, 3 action, unless you have triples, right? So the sample space is not the same as this, right? I can borrow from number 15. So it's going to be like B, 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 boy, 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 right? And boy, 1 boy or 2 boy will be BBG, BGB, and then what, GBB, right? That's the 2 boy, and then I can count 1 boy. 1 boy is going to be BGG, and then what, GBG, and then GGB, right? That's 1 boy, and no boy means GGG, all girls, right? So if it's 3 children, your letters have to be 3, right? And so if this is counting it, in the old-fashioned way, but I can also count it by the fundamental counting principle. It will be 2 times 2 times 2. It should be 8. Is that 8? Let's count 1, 2, 3, 4, 5, 6, 7, 8. Yes, I didn't miss any. So 8 is my sample space, right? So which way do you want to count? This is the fundamental counting principle, right? And or you can just write it all out. It's up to you which way you want to count. Now the event had to be from the sample space, right? The event had to be from the sample space, and it says precisely 1 boy, right? Precisely 1 boy. Which one out of this sample space is precisely 1 boy, right? So this is 3 boys, 2 boys. Precisely 1 boy is this one here, this one here, and this one here, right? And so that's B, G, 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 B, G, and G, G, B, right? So our cardinal number of the event is 3, right? But is there any other easier way to do it, right? Remember in chapter 12, we say if it's specific characteristic, then we can use the distinguishable permutation, because this is 1B and 2G, right? So how many ways can you count these letters, right? So that's the distinguishable permutation way of counting, right? If you want specific, not all, right? So specific, you will do what? 3 letters, so it's 3 factorial. You remember this from chapter 12? 3 letters, 3 factorial, and then how many of the letters are repeated? Only 1 B, right? But 2 G's. So you will take away the repeat letter orderings. That doesn't matter. So 2 factorial. And if you simplify this, it will give us the 3. So it agrees, right? So do you want to count it by looking at the sample space, Or do you want to count it by, what we learned in chapter 12? It's up to you. It's up to you. Sometimes it could take very, very long time to list down all your sample space and all your event, right? So anyway, let's finish up the probability, right? That's just counting. The probability is having one boy, right? One boy in 3 children family in our sample space is what? Event is cardinal number of 3 and the sample space is 8, so it's going to be 3, 8, right? Does that make sense? Okay. So number 17, same thing, is 4 children, right? So 4 children, you can list it all out, right? B, 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 that's 4 children, right? You G, 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 that's another one, right? And you can keep counting, right? So I'm a little lazy now. I can keep going and count like that, right? So it can be like G, B, 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 and B, G, B, B, things like that, right? But I'm going to get lazy if I'm counting all of them, right? So last time in chapter 12, we say if we are counting all of them, that is the sample space is all of them, we can use fundamental counting principle to count all of them, and that's 4 actions, right? 4 actions, 4 children, 4 actions, so it's going to be 2 times 2 times 2 times 2, and that's going to give us the 16. Yes, you are right, 16. That is the cardinal number of the sample space. But if with a specific characteristic, we say we're not going to count with fundamental counting principle, we're going to count as the distinguishable permutation, and that is our event, right? So our event is what? 2 boy, right? 2 boy in a 4 children family. So that is going to be using write down the boy, boy, girl. Girl is the 2 boy, right? Right? Because you have 4 children, you have to have 4 letters. So this is one of them, but how many ways can I rearrange them, right? So this is this distinguishable permutation way of counting if they give us the specific characteristic and not counting all of them, right? So that's going to be how many letters altogether? 4 factorial for the 4 letters. And how many of the letters repeat? 2 factorial for the 2 B's. And then 2 factorial for the 2 G's, right? So write it out, 4, 3, 2, 1, 2, 1, and then another 2, 1. So this 4 cancel with this is 4, so that's going to be 6. So yeah, you can write it out. You can try to see if you can rearrange B, B, G, G, the 2 boy cases, how many of the arrangements can you get? You will get 6 if you counted it right, right? So the 2 boy in the 4 children family will be what? The event, cardinal number of the event, 6, cardinal number of the sample space, 16, and so that reduced to 3, 8. 3, 8, that's right. Okay, so hopefully that helps. And if you are still having trouble, I'm going too fast, it doesn't make sense, any reason, just reach out, okay? I would love to hear from you, and see you soon. Thank you for watching. Thank you very much.